Hey, Calc students, this is Mr. Beck. Today we're going to be talking about two different topics. Number one, we're going to be talking about indeterminate forms and how indeterminate forms of limits and how we could find those limits according to what's known as L'Hopital's rule. And then we're also going to talk about improper integrals. So let's get started. Now, if you remember back in chapter 1, we talked about different limits, and we had something like the limit as x approached, say 3 of x squared minus 9 over x minus 3, where if we tried to plug in the 3, we will get what's known as an indeterminate form, 0 over 0. As 0 over 0 is indeterminate, so we had to figure out another approach to this problem. So what we did was we took the limit as x approached 3. We said that was x plus 3 over x, or times x minus 3 over x minus 3. And then we reduced these and said that limit's equivalent to just the simple limit as x approaches 3 to x plus 3, which now we could plug in our 3 for our limit and we get 6. So that was way back in chapter 1 before we did a lot of our calculus, and this is really the basis of calculus. Now that we know some calculus, we can find some other ways to do some indeterminate limits. And that's called L'Hopital's rule. The first one that I want to look at is this limit as x approaches 0 of e to the 2x minus 1 over e to the x. So what I'm going to do is I'm going to open up Desmos. And in Desmos, I'm going to first type the function e to the 2x and then minus 1. So the exponential function, which is right here. So e to the 2x minus 1. I want to take a look at that limit, and then I want to take a look at the limit x. So going back to what I was talking about was we want to know this limit where if I plug in 0, I will get 1 minus 1. So if I plug in 0, I get 1 minus 1 over 0, which leads to the indeterminate form. Now, I don't like to equate, and in fact, it's kind of important that we don't ever actually equate this limit. Never say this limit equals 0 over 0. That's absolutely bad. You're going to lose a lot of points if you do that. So don't say equals 0 over 0, but it's good as notation say 0 over 0 is indeterminate, because that's why we can use L'Hopital's rule. So when I take a look at this, e to the 2x minus 1 and x, when I take a look at these two functions, we can see that as x approaches 0, we end up with that 0 over 0, which is what we were talking about before. Now, what I'm going to do is I'm going to zoom in, because by zooming in, that's the numerical and graphical approach to taking the limit of a function. So as we zoom in, I'm going to zoom in hopefully sufficiently. Now when we take a look at these two functions, we're going to say, okay, this is 0 over 0 when x approaches 0. That's true. Let me see if I can move. Oh, I locked my screen. Not sure how I did that because I've never done that before. Okay, so we get 0 over 0. Now, what I want to do is look at this blue graph and say, okay, not what happens at 0, but what happens as we approach 0. So as we get smaller and smaller, this of course gets smaller and smaller, and so does the red one. But more importantly, let's take a look at what happens when x is the 0.001 we see here. On the blue graph, the y value is also 0.001, but on the red graph, it's 0.002. As we approach 0.02, on the blue graph, which is x, we get 0.002, which hopefully makes sense because this is y equals x. On the red graph, we get 0.004. Now what's looking like is we have, these look like two linear functions. Now the blue one is linear, the top one is not linear, but as we get really, really close, they both look linear. And what it looks like is the ratio of these two numbers will always be 2. If I zoom in even more, so let's zoom in some more. By zooming in some more, the ratio of the red graph over the blue graph should equal 2 the entire time. And that's really what we care about. We care about what's happening as we approach, not actually what happens at that value. So what this means is by taking an approach of what's happening as we approach it, it's kind of the rate at which we're approaching it. When we say the rate at which we're approaching it, then that's what gives birth to L'Hopital's rule. L'Hopital's rule says if we end up with an indeterminate form, and the indeterminate form is all of these types of indeterminate forms up here, we're going to see a bunch of those. But as we take a look at those indeterminate forms, if we ever yield one of those, specifically the ratio ones, then we can use L'Hopital's rule, which says the actual limit that we care about is equivalent to the limit of the rate of the top function over the rate of the bottom function, which is what I just showed you in Desmos, that it's how we're approaching. If you remember, it was a 2-to-1 rate. So if we take a look at L'Hopital's rule, because this yielded an indeterminate value, what I did was I used L'Hopital's rule to say the derivative of the numerator is 2e to the 2x, the derivative of the denominator is 1, and now when we plug in our 0 in for x up here, we get 2e to the 0 over 1, which is just 2. Now we saw that graphically that the ratio of the red graph over the blue graph was 2. And that's because we were examining the rates at which they approach. Problem number 2. First thing is when we plug in infinity here, the natural log of infinity is infinity. Infinity in the denominator, we get our infinity over infinity indeterminate. Now what I'd like to do is go back to Desmos, and now I don't care about that top function. What I care about is the natural log of x. The natural log of x, and it's not going to be as we approach 0, it's as we approach infinity. Now I'm going to squish this down a little bit, but as we approach infinity, what's the ratio of these two infinities? Which infinity is bigger and why? And what we can see is the natural log of infinity is a much smaller infinity than just infinity itself. So the ratio of these two infinities, the green infinity is smaller than the blue infinity, and which leads to another beautiful discussion at some point. But the ratio of these two infinities, the natural log of infinity is significantly smaller than the actual infinity itself. So what does that mean? The ratio of these two values is going to be a much smaller number over a much bigger number, which should in turn actually equal 0. Now we can show that through L'Hopital's rule because the rate at which we are changing, the rate at which we're growing of the natural log function is the 1 over x, and the rate at which we're growing of the linear function is just 1. So 1 over infinity, we know it's really, the limit as x approaches infinity, 1 over x does actually equal 0 over 1. That 0 over 1 does equal 0. Now, so we could simplify this approach as x approaches infinity by saying which one grows faster. If we start lumping the categories of which function grows faster, it might make a little bit more sense to our problems. So linear functions linear functions tend to grow faster than natural log functions. On number 3, without showing you what the work is, e as x approaches, wrong tool. As x approaches negative infinity, this denominator becomes e to the infinity. The exponential function, or all exponential functions, will grow faster than polynomials. So e to the infinity and infinity squared, the e to the infinity will win out because it's going to grow faster. And that idea of growing faster, again, gives birth to what L'Hopital's rule is about. It's how is it growing. Now, if we apply L'Hopital's rule, the derivative of the numerator is 2x, the derivative of the denominator is negative e to the negative x. Now, hopefully, like I did, we actually checked that this gave us an indeterminate form. But now, what's going to happen is this is going to give us another indeterminate form, negative infinity over negative infinity. So we can use L'Hopital's rule again. Now, L'Hopital's rule, I failed to mention, but I'll say it right now. We tend to put L'(h) over that equal sign. You don't have to, but we tend to do that because it's a little bit more descriptive of why these two limits are equal to each other. But we can use L'Hopital's rule again, and then using L'Hopital's rule again, the derivative of the numerator is 2, so the rate at which that linear function is growing is just in the constant value. The exponential function is still growing exponentially, but now when we apply that limit, we will get 2 over the limit as x approaches negative infinity of e to the negative x. That limit is infinity itself, so 2 over infinity does give us 0. On problem number 4, what we see here is if we plug in infinity, we essentially get 0 times some form of infinity, which is indeterminate. So our first step is how do we rewrite this? And this is so that we can apply L'Hopital's rule. And by rewriting this is negative exponential. So let's go ahead and put that e to the x in the denominator. Now it's infinity over infinity. Then infinity over infinity means L'Hopital. So we L'Hopital it. Derivative of the numerator is 1 over 2 squared of x. The derivative of the denominator is e to the x. And now when we apply, or we take the limit as x approaches infinity, we will get 0 over infinity, and 0 over infinity is itself 0. Now, what I did here was I kind of simplified a little bit of the algebra. Now, is it essential? No, because we've got the 0 over infinity, which tells us that's 0. Problem number 5. And what you can see here is a little bit of the note that I talked about earlier. But problem number 5, as x approaches infinity, we have a quadratic function over a little bit more of a complex function. So this is in essence infinity over infinity. Notice how I'm never actually saying equals infinity over infinity. That's bad. I'm just saying, okay, mentally I know this is an indeterminate value. So I apply the L'Hopital's rule. Derivative of the numerator is 2x. The derivative of the denominator is this expression, which then when I rewrite it algebraically, and I take the limit as x approaches infinity, we do get infinity, because 2 times infinity is infinity. Problem number 3, the limit as x approaches 0 of x cubed over cotangent of x. Once again, this is indeterminate, 0 times infinity. That indeterminate means, can we rewrite this so that we can apply L'Hopital's rule? Cotangent is the same thing as 1 over tangent. So now we take that limit by L'Hopital's rule. Derivative of the numerator is 3x squared. Derivative of the denominator is secant squared of x. So 3 times 0 over the secant of 0 is 0. Now, we do have a special technique when it comes to some specific indeterminate limits. This is a very, very famous indeterminate limit. The limit as x approaches infinity of 1 plus 1 over x to the x. This limit, most, or many students, I shouldn't say most, many students know that this limit does equal e. The big question is, why does this limit equal e? Let me show you. So what we're going to do, and this is a special technique that if we have like 1 to the infinity power or 0 to the 0 power or things that happen like that, what we could do is we could set that limit equal to just some random variable, which we're going to call L, which represents the limit. Now, what's prompting this is I have this special kind of function and some form of x to the x power. And if you remember, we did this when we did some derivatives. So we did a logarithmic differentiation. This is kind of like logarithmic limits. We take the natural log of both sides, and the benefit of taking the natural log of both sides. Notice how I did bring the limit on the outside because limits are cool and they can do that. But anyway, the reason why we did the exponential function is, or that logarithmic differentiation, logarithmic limits, eventually I get the right terminology there, is we could bring that x out into the front. And now this is going to be infinity times 0 in essence. But what we're going to do with that x is we're going to turn it into 1 over x in the denominator. So now we can apply L'Hopital's rule. And in applying L'Hopital's rule, the derivative of the natural log function, remember, is the derivative of what's inside over what's inside. Now the derivative of our new green denominator here is also negative 1 over x squared, which does simplify here to 1 over 1 plus 1 over x. Now the limit there is going to be 1. The limit on the other side is still the natural log of the limit. So now if we take e to both sides, we'll get our limit as e. Now, one of the reasons why I like going through this specific problem is, I'm not sure if you remember, when we talk about compound interest, or compound, I guess interest is probably a better way of saying it, 1 plus r over n to the nt power. One of the special things we could do with that is we could say this is 1 plus 1 over n over r to the n over r times rt power. Now, what happens as, and for compounding, what's the limit as n approaches infinity, meaning we're compounding more and more. This is e, so that's where we get p times e to the rt, or that Pert equation for continuous compounding. So I like to show the problem for that reason. Now we do have another problem. This is the sine of x to the x power. So the sine of 0 is 0. What is 0 to the 0 power? 0 to the 0 power. We can determine that by, once again, setting that equal to L. Take the natural log of both sides, and you can see that I automatically brought that x out in front. And I did take the limit and pull on the outside because limits are really the most powerful functions. So once again, we can write that x as 1 over x in the denominator. And now I didn't actually show it, but actually, no. Oh, yeah, L'Hopital's rule equals the, by L'Hopital's rule, these limits are equivalent to each other. So the derivative of the natural log of sine is the derivative of what's inside over what's inside. Denominator is negative 1 over x squared. And now when we plug in 0, we will get cosine of 0, which is 1. So 1 over 0 over 1 over 0. Now we could algebraically simplify that if we really wanted to. And in fact, that's what I did. That numerator is what we call a cotangent. So we could turn the cotangent in the numerator into tangent in the denominator. We could turn the negative 1 over x squared into, in the denominator, into negative x squared in the numerator. And now we can keep going, take L'Hopital's rule again. And we're taking L'Hopital's rule again because we have 0 over 0. And in doing so, we now have negative 2 times 0 over the secant of 0, which is 1. So 0 over 1 is the natural log of our limit. So e to the 0 is 1. Turns out 0 to the 0 power does equal 1 in this case. Problem number 9. Now, this series of problems that we're coming up with are going to be problems that we did way back in chapter 1, but now when we apply L'Hopital's rule, it tends to be a little bit more efficient. So first thing that I did was I combined these together into one expression so that I could use L'Hopital's rule. Derivative of the numerator, derivative of the denominator. Now when you plug in 0, if you remember, the limit as whenever you get 10 over a 0, in this case, it's a number very, very close to 0 on the positive side, we do get infinity. If that was on the negative side, we'd have negative infinity. Problem number 10, we get 1 times 0 over 0. So derivative of the numerator, derivative of the denominator. So this ends up just being 0 plus 1. Now, ironically, I do think this problem is a little bit easier to do based off of what we learned in chapter 1 by breaking it up into the two limits. This one's sine of x over x, and 1 plus x over, really just 1 plus x. So the limit of the second portion is 1, so you just get 1 plus 0. Anyway, these problems, to do them properly, we would have to do like a special or anyway, turn this into sine of 3x over x times x over the sine of 4x and do some work with that. But L'Hopital's rule saves us all that additional work. So the derivative of the numerator is 3 cosine 3x, derivative of the denominator is 4 cosine 3x. So now when we plug in 0, we do get 3/4. Problem number 12, this is one of those that we could factor. We could use SOAP and x minus 2 times x squared plus 2x plus 4. Or, because this is 0 over 0, L'Hopital, and we get 3x squared over 1, plug in 2, we get 12. One more time, this is something that we could factor, but now that we apply L'Hopital's rule, derivative of the numerator is 4x, derivative of the denominator is just 1. So as x approaches negative 1, we do get negative 4. Now keep in mind, the only reason why this is going to work is because this does give us a 0 over 0, which is indeterminate. Now, remember, never ever set it equal to 0 over 0. That is bad. No, don't do that because you can never set a determined value equal to something that is not determined. So don't ever put equals 0 over 0. Problem number 14 is our basic. This one we should know right away that limit's 1, but L'Hopital's rule allows us to skip over the definition of limit, or what we used. I guess we used squeeze theorem on this one when we found this limit in chapter 1. Some AP specific problems. If you see that we can apply the special approach, and that's because we have an x to an x power. That's what triggers me to say that, hey, this is our special approach. And then you've seen that approach a couple times now. In the end, we're going to get e squared as our limit. I'm going to slowly walk through these ones a little bit, or really not walk through the entire thing because we've applied concepts already. But L'Hopital's rule, derivative of what's inside the natural log over what's inside, derivative of the denominator is 1. And now if we take our limits at h approaches 0, we do get 1/2. I like this problem right here because right now, if you remember, when we plug in 0 for h, we're going to get the integral from 1 to 1. So the integral from 1 to 1 is always going to be 0. So this does give us a 0 over 0 mentality. L'Hopital's rule means that we are going to use the second fundamental theorem of calculus. If you remember second fundamental theorem of calculus, when we take the derivative of the integral, we plug in the upper limit times the chain. The chain is going to be the derivative of 1 plus h, which is 1. And now we plug in 1 and multiply by the chain, which is 0. So really, we now have this limit that we see right here. So now when we plug in 0 for h, we are going to get the square root of 1 plus 8. And the square root of 1 plus 8 does give us, excuse me. This problem generated a lot of anger when it came to the AP test, because this was an AP problem on a free response. So this generated a lot of anger, mainly because a lot of students did the wrong thing. A lot of students right here said, hey, this equals 0 over 0. And the moment you do that, you suddenly lose a lot of points. Have you heard the theme yet? Don't ever write 0 equals 0 over 0. It's okay to kind of reference what you're doing. In fact, what I would almost encourage is not even put that arrow there. Just say, you know what, we know that 0 over 0 is indeterminate. It never actually equals 0 over 0. Moving right along. So when I do this problem, I do see that I have indeterminate form. By having the indeterminate form, applying L'Hopital's rule, g prime over 6 times x plus 1. Now, g prime, do I know g prime? I know that y is equivalent to g of x, which means that dy dx is our g prime. So this does equal g prime of x. And so g prime of x at the point -1, 2 is what I did here. And I found g prime of x at -1, 2 equals 0. So when I take a look at my limit, I'll bring that back on the screen. One more time, I have a 0 over 0, which is indeterminate, which means I have to apply L'Hopital's rule again. So g double prime over 6. Now, what is g double prime of 1? Well, to find g double prime of 1, I need to say g double prime is going to be my second derivative of the differential equation, or really the derivative of the differential equation that I have there, which is 2x minus 1/2 dy dx. Now, what I did was I just showed the notation that the derivative at the point that we care about is -2. So now when we apply that limit, we get -2 over 6, which is -1/3. One of the important things that I do want to reference is, please, this is all of your linking information, specifically right here. Let me kind of outline that. This right here is your linking information, that you're linking the ideas together. We have differential equations. We also have L'Hopital's rule that involves functions. So we're kind of merging two different notations. And yes, they do mean the same thing. But please, please link all of your information together whenever you're doing a free response problem. All right, moving right along, comes to improper integrals. When it comes to improper integrals, the idea for improper integrals, well, what is an improper integral? The improper integral is what happens when you take the integral to infinity. So if you're taking the integral to infinity, meaning we're adding an infinite area underneath the curve, it's improper because you can never actually reach infinity. And keep in mind, this is a definite integral. And as a definite integral, we should have a definite value. But if we're going to infinity, that's not a defined value. So how do you get a definite value for an undefined place? And that answer is we can't. And since we can't, this is where we're going to say, okay, we're going to use our definite integral to a variable, but then we're going to say what happens when that variable goes to infinity. So when the limit as we go to infinity. And that way, by applying a limit mentality to this, then we're going to be able to find the overall value. So this is going to be very, very helpful, especially when you have a situation like this, where what happens when, again, we're adding the integral from 1 to infinity of our function here. So for the class that I was working with, they chose the variable star. Typically, I'm going to use the variables either A or B. I tend to not use C because we are still integrating, and when you integrate and you have the plus C, it could get confusing. So I tend to use either A or B. You'll see that I did that over for the next series of problems. But for this problem, we chose star because why not? Star's cool. Anyway, by taking our limit, we turned our definite integral into a limit of an integral. We found the antiderivative of that integral. And once we found the antiderivative of the integral, we went ahead and plugged in B, plugged in A, or really our upper limit and our lower limit. And now, by rewriting it, the limit of this expression does equal 0. And then 0 plus 3/4 does give us 3/4. So what this means is we are able to find or like add up a bunch of infinite values. And when I say that, what I'm kind of referencing is the 3 over x to the 5th. It's going to be a really, really small value. But remember, we did this by Riemann sums, that we're saying eventually we are going to have a countable amount of rectangles that we are going to be able to add together. Now, this idea is going to lend us or lead us into chapter 8. And in our chapter 8, we're going to be talking about sequences and series, and eventually we're going to have infinite series, and we're going to find the sum of an infinite series. And by finding that sum, really it translates into, or we're going to use integration to do that too. But anyway, I'm getting ahead of myself. So on to problem number B. What you can see here is I did say the limit as b approaches infinity. I guess this is problem 2. The integral from 0 to b of our expression. I did this one by integration by parts. So uv minus the integral of v du. And went ahead and I found the second integral right there. And now I'm going to plug in my definite values. So that's plugging in b, plugging in 0. Now the limit of these two expressions are both 0. One of the ideas that the AP does require you to have is the limit as b approaches negative infinity of e to the x. You are expected to know that limit is 0. Anyway, the fact that this limit does equal 16 means we have what's called convergence. And we have convergence because we are able to find the actual limit. That's something I skipped over on the previous problem, so I apologize. Problem number 3, I did a u substitution. With the u substitution, I now have this expression. I'm taking the limit as b approaches infinity, the integral from 1 to b. I found the integral, plugged in b, plugged in 1, and now I'm going to be taking the limit, and that limit does give us 1/2. And because the limit is a definite value, this integral converges. Problem number 4. Once again, I did a u substitution on this problem. With the u substitution, don't forget that du is 2x dx. So 1/2 times that integral. Now this is an improper integral. I'm integrating from 1 to infinity. Once again, took the limit as b approaches infinity. And everybody, I understand this is kind of annoying to write it over and over again when a lot of us would like to say the natural log of infinity, et cetera, et cetera. We have to be careful that we don't write those kind of things because those are indeterminate values. But anyway, going back to the problem, 1/2 natural log of u, plug in b, plug in 1, now take your limit. Because our limit is infinity, this integral diverges, meaning we can never count the area underneath that curve. Now, for those of you who are wondering, the 2x over 1 plus x squared, what it looks like, use Desmos. This video is getting long enough. All right. Problem number 5, u equals e to the negative x. If u equals e to the negative x, there's my du. This turns into an arctangent problem. I turn it into an arctangent problem. So the arctangent of u going from 0 to a. And the reason I went from 0 to a, keep in mind, this is where I guess I probably need to say something about this. The limit as a approaches infinity. If a is approaching infinity, e, I didn't actually write this, which kind of is weird. All right, so as x approaches negative infinity, e to the negative x, or how about, let me just write that as u approaches 0. Nope, I take that back, that one's infinity. So as x approaches infinity, u approaches 0. And by writing it that way, that's why I have this integral from infinity to 0, which is still improper. Notice how I do have a negative here, so I rewrote it. So I went from 0 to infinity, but this is where I plugged in a's, or limits a approaches infinity. So then we have our arctangent problem. Now back on track, that the arctangent of a minus the arctangent of 0. Now, what is the limit as x approaches infinity of arctangent of x? I probably shouldn't use x. Let me go ahead and use a because that's what I said. This is pi over 2. You're expected to know arctangent limits. The graph of arctangent of x will look something like this, where we have two horizontal asymptotes. two horizontal asymptotes. This one is pi over 2. This one is negative pi over 2. So you're expected to know as a approaches infinity of arctangent of x, or as a approaches negative infinity of arctangent of x. But then we get pi over 2, which is a value, so it converges. For the next series of problems, I want to take you to a very, very brief discussion of what is the integral from -1 to 1 of 1 over x dx, where if you take a look at this graphically, and by the way, this is a very, very fun problem to argue in class because people get so passionate about this, which is hilarious. So the integral from -1 to 1, we're going to have this integral looks like this. Most students look at this and say, okay, this is a negative value. This is a positive value. And because this is a negative and a positive value, and those two areas are equivalent, a lot of people say, well, shouldn't that equal 0? And the answer is, well, it probably should, but we can never know. The reason why you can never know is because each one of these areas is an infinite area. Because they're infinite areas, we can never actually count them. And because we can never actually count them, we can never guarantee that we're going to get 0. So, is this true? Probably, but we don't know. And a lot of people still say, okay, but because everything I know, it should still equal 0. And then here's what I'm going to argue. We're not guaranteed that we are approaching 0 at the same rate. And what we should be prepared for is, okay, x is approaching these values, but we don't know how fast they're approaching, aka L'Hopital's rule. Since we don't know how fast they're approaching, we're not actually guaranteed what's going on. A lot of people still say, okay, shouldn't they approach at the same rate? Well, this is when I start introducing parametric equations. Parametric equations means that we can start approaching at different speeds from different sides. So we'll never actually know. It probably, in fact, the principal value of this should be 0, but we're not guaranteed that it's going to be 0. So there was a problem on the AP test that was very similar to this, where the limit does not exist. And because the limit does not exist, we really don't know. All right, so what's the point of this? If we have an infinite discontinuity, aka that infinite discontinuity is going to be a vertical asymptote. So if we have a vertical asymptote, then what we have to do is we have to rewrite this so that we once again have the definite value. And where we can see this is, let's take a look at the graph of secant. If you remember quickly, the graph of secant, at least the part that we care about, is going to look like this. So as x approaches pi over 2, this goes on to infinity. Because it goes on to infinity, once again, this is really an improper integral because we can never find the secant of pi over 2. Since we can't find the secant of pi over 2, once again, turn it into a definite integral where we are now saying what's the integral as we approach that value. So as we approach that value, the secant of pi over 2, once again, we don't actually know what that is. So what we could do is we could turn that into 1 plus sine of b over cosine of b. And for those of you who are wondering how I got that, 1 over cosine of b plus sine of b over cosine of b. That's where I turned it into the expression. And yes, the natural log 1 is 0. So this is where I could apply. Do I need to apply L'Hopital's rule? No, we can just directly plug these in. There are going to be times that we will have to apply L'Hopital's rule to be able to find this limit, which is why we connect 7.7 and 7.8 together, because L'Hopital's rule is going to be important for us to be able to find these limits. So in this expression, I could recognize that this is going to be an improper integral because we can never actually integrate from 0 because we have an undefined value on the left side. So we're going to say the limit is a approaches infinity. A approaches 0 from the positive side. Let's go ahead and find this indefinite integral, and then make it definite, and then apply our limit, which does give us 6. So because we can find the limit, this does converge. On our next expression, so from -3 to 1, a lot of people will look at this and say, okay, should this be improper? Well, if we plug in -3 to our denominator, we now have a number over 0, and that's what makes it improper. So we're going to take the limit as a approaches -3 from the positive side. So as a quick visual, so we're integrating from -3 to +1. So -3 to +1. Our lower limit is going to be approaching -3 from the positive side, where maybe there's a case where the upper limit is going to be approaching 1 from the positive side. But anyway, going back to the actual problem. All right, we have our limit. Let's go ahead and find the integral. The integral is -1 times 9 minus x squared to the 1/2. And I did this by u substitution where u equals that denominator. But anyway, when we plug in 1, you get -2 squared root of 2. When we plug in our limit of -3, you get 0. So this is -2 squared root of 2, which converges. For this problem right here, this is kind of similar to what we already did, but this case, now, if we would have gone from, say, negative or from 2 to infinity, we would have to split this up into 2 integrals. Kind of occurs to me that we didn't actually split this up into 2 integrals. We could do that for the next problem. But anyway, so if u is 9 minus x squared, du is -2x dx, u substitution. So as x approaches 4, u is going to approach -7. As x approaches infinity, u approaches -infinity. We can flip this around, or I guess keep it as it is, which is what I did in this problem. But indefinite integral, make it definite. Then we have infinity to the 2/3 is infinity, so this is a non-existent limit. This one is what I was referencing, very similar to the problem that we had before, where because we have an infinite discontinuity, the infinite discontinuity means we are going to have to break it apart into the sum of two different limits. So -1 to a, where a is approaching 0 from the left, a to 1, where a is approaching 0 from the right, 3 over x squared, which if we integrate 3 over x squared, we get -3 over a. Now when we try to find that limit, we do get -3 over 0, which is an indeterminate value. So this value is non-existent. So what are the key concepts that we need to take away from this? The key concepts we take away. Number 1, we never ever, don't ever equal 0 over 0 or infinity over infinity. If you do that, bad things will happen, so don't ever do that. Number 2, if we are trying to integrate an expression that has a vertical asymptote in between, we must break it up into the first one plus the second one, and then see if we could do either or both of those. Number 3, if we are integrating an expression to infinity, we have to break it up into a limit. Or if we are going to be evaluating just to an asymptote, we have to once again, if we want to evaluate the integral either from an asymptote or to an asymptote, vertical asymptote, then we have to break it up, or we have to apply it to the limit function. And I think I've been talking way too long, so hope you guys have a great day.